Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. Today we're going to look at a key concept in understanding and reporting data: standard deviation. Standard deviation allows us to say how much variance or spread there is in a set of data and is related to precision. And how is that precisely? Well, you'll need to get a drink and carry on watching to find out. As I noted in the video about central tendency, link below of course if you haven't seen it, we make measurements in order to characterise a sample, and we don't just make single measurements because there will always be random errors in any experiment. Therefore, we repeat our measurements a number of times, such that we might be able to quantify how large the errors are. This is especially important when comparing two sets of data. For instance, how a group of patients given an analgesic rate their pain relative to a control group. If the errors in a measurement are larger than the difference between two sets of data, then we cannot say with certainty that they are different. This is the entire basis of hypothesis testing, as we will look at in a separate video. There are two main types of error that may be introduced into a measurement: a systemic error and a random error. A systemic error is something wrong with the system being used for measurement. For instance, a miscalibrated instrument or a set of standards prepared incorrectly. As long as the measurement is made repeatably, a systematic error will result in data with a central tendency that is incorrect. That is, not close to the true or expected answer. Such data would be inaccurate. Random errors, conversely, and as the name implies, are unpredictable and may increase or decrease a measured value, with both outcomes being equally likely. The outcome from a random error, therefore, is that the measured data will be spread apart from each other, although the central tendency, assuming there's no other systematic error, should be near the true value. The larger the error, the more the data will be spread apart. Thus, we can assess how large potential errors are by quantifying the amount of spread or variance in the data. We do this with a function called the standard deviation. Ordinarily, I would take a little time to explain how a certain parameter is derived. However, in this case, I have to admit that knowing how standard deviation is derived really adds little to your understanding. I think it's much easier simply to show you the equation for standard deviation, and then we can talk about what it means. And here it is. Looks a little scary, I accept. But as usual with these things, a lot of it is a mathematical notation, and it's really not that bad. The standard deviation itself is given the symbol sigma, which is S in the Greek alphabet. And it is calculated as the square root of the sum of each data point, xi, minus the mean, mu, squared divided by the total number of data points, n. If you say it quickly, it doesn't sound too bad. Also, most calculators have built-in functions that do the calculation for you. All you have to do is enter your data and press a button. Now you know what the calculator is doing when you press that button. One technical point before we move on. When we make a measurement on everything in a sample, for instance, if we were to determine the drug content in every tablet from a batch of 100,000 tablets, we are analysing the population. When we calculate the standard deviation in data from a population, we use the symbol sigma, and we use the total number of data points n in our calculation. As you might imagine, it is far more likely that we are dealing with data on a much smaller subset of a population, which we call a sample. When we calculate the standard deviation in data from a sample of a population, we use the symbol S, and we replace n in the equation with n minus 1. It seems a small and kind of pointless change, but it does in fact make a difference. And because I'm a pedant, I thought I'd mention it. You can see this on your calculator, in fact. Calculators have a button for sigma and a button for s, or sometimes n and n-1. Now you know what they're for calculating the standard deviation of a population or a sample, respectively. Let me show you some real data to illustrate a standard deviation. Here are some drug content values for 15 ibuprofen tablets taken at random from a large batch. Each tablet should contain 200 milligrams of drug, and the mean of the data is 200.2 milligrams, as I discussed in a separate video. How do we calculate the standard deviation? We enter the 15 values into our calculator, press the S or n-1 button. We are dealing with a sample set of data, remember? And the answer comes out as 2.01 milligrams. What does a standard deviation actually mean, I hear you ask? And that is a good question. It describes a fraction of your data, and we report our values as a mean plus or minus the standard deviation. So, for the tablet content data I am using, we have a mean of 200.2 milligrams plus or minus 2.01 milligrams. Many people assume that the range encompassed by a mean plus or minus a standard deviation is 95% of the data, but that is in fact wrong. A mean plus or minus a standard deviation covers around 68% of the data. 95% of a data set is actually described by a mean plus or minus 2 standard deviations. I bet that surprised you, because most people don't know that. So, by watching this video, you've propelled yourself into the top level of analyst. If that doesn't warrant a like button, I think we're only left with bribery. Incidentally, we will look at why we need 2 standard deviations to describe 95% of your data in the video on distributions. For now, we need only to know what a standard deviation is and how it is calculated. I said earlier that the mean is related to accuracy. If the mean of a set of data is close to the expected or true value, then the data are accurate. Standard deviation is, conversely, related to precision. If the standard deviation is small, that is, there is little spread in the data are tightly bunched, we say they are precise. This is why accuracy and precision are not the same thing, as I discuss in the video on accuracy and precision. If you watch that video, you will see how looking at data and determining whether they are precise and or accurate, or neither, allows you to say a lot about how the data were recorded. One other point to finish. I hope you can see that the value of a standard deviation is going to be related to the type of data being measured. For instance, in my example of tablet drug contents, the data are in milligrams and the standard deviation is in milligrams. The larger the variance, the larger the standard deviation value. Therefore, we can express the standard deviation as a percentage of the mean, like this. When we do that, we term the value the coefficient of variance, and it's a useful term as it expresses variance as a percentage value. The higher the value, the greater the spread, but it normalises for any data set. Right, we are done. Standard deviation is reported alongside a mean and it expresses variance in the data. A mean plus or minus 1 standard deviation covers around 68% of the data. 95% of a data set is actually described by a mean plus or minus 2 standard deviations. We can express a standard deviation as a percentage, in which case it's called a coefficient of variance. I hope you found that useful. If you did, please tell your friends and colleagues about the channel. And if you have suggestions for topics, please let me know in the comment below. Otherwise, thank you so much for watching, and I'll see you again soon.